Over 16 centuries of torrential monsoons, intense heat waves, and winter humidity have eroded the stone temples of the Indian subcontinent. Yet amidst this environmental punishment, one metal monument remains remarkably pristine. This is the Iron Pillar of Delhi. It is a massive 6-ton cylinder standing in the courtyard of the Quwwat-ul-Islam Mosque. Thermodynamics dictates that a structure like this shouldn't exist. Exposed iron naturally reacts with oxygen and moisture, aggressively degrading back into red powder. It is easy to assume a piece of metal capable of surviving this long was cast in a single perfected pour, or forged from a highly advanced pure alloy. Modern spectroscopy reveals a different reality. The iron is saturated with heavy chemical contaminants and physical debris trapped within the metal matrix. Chemical mapping suggests that these physical defects are the mechanism keeping the structure intact. This illustration details the ancient Gupta bloomery process. Blacksmiths horizontally forge-welded hundreds of glowing, solid chunks of iron together. Looking at the clay furnace on the left, these pits operated at lower temperatures than modern blast furnaces, preventing the iron from fully melting. Ancient Indian metallurgists also omitted a step we rely on today. They did not add limestone flux to the furnace, an ingredient used to draw impurities out of the metal. Without that flux, the iron remained saturated with high levels of phosphorus and microscopic glass-like shards of unrefined slag. This composition inadvertently loaded the iron with the specific chemical tools it would need to defend itself against the atmosphere. When the pillar was first erected, those trapped slag particles accelerated the initial decay, creating intense, localized corrosion across the surface. As the surface iron dissolved, the phosphorus did not wash away. It stayed behind, rapidly concentrating and altering the typical cycle of flaky, porous rust. This diagram shows the cross-section of the pillar's surface. The concentrated phosphorus catalyzed the growth of that smooth orange layer, a dense amorphous barrier known in materials science as misawite. Misawite provides some initial defense, but it requires specific environmental stress to transform into a permanent shield. During Delhi's heavy monsoon nights, the 6-ton mass of the iron retains colder temperatures. It acts as a thermal condenser, pulling thick moisture directly onto the misawite surface. Then the harsh Indian daytime sun strikes the metal, causing temperatures to spike and baking the surface dry. Returning to the diagram, you can see the result of those wet-dry cycles. The thermal shock forces the misawite to crystallize into the green layer shown here, iron hydrogen phosphate hydrate. It forms a physical seal against oxygen and water. The pillar is enveloped in a specialized, self-healing skin of rust, powered by the local weather. This chart highlights the mechanical penalty of high phosphorus iron. The alloy suffers from a defect called cold shortness, leaving it brittle with a ductility of only 5%. Modern structural steel stretches up to 25% to absorb stress. If you attempted to build a modern bridge with the pillar's alloy, the supports would snap under tension. The lower diagram illustrates a historical stress test. In 1739, an invading army fired a heavy artillery cannonball at the shaft at point-blank range. Despite the metal's brittleness, the massive, uneven, slag-filled microstructure absorbed the kinetic shock. The cylinder dented, but it did not shatter. Ancient smiths used this durable, brittle alloy for a specific architectural role, a vertical monument designed to support nothing but its own weight. This graphic demonstrates how the pillar's chemistry became a blueprint for modern materials science, leading to the development of weathering steels like Corten. Modern engineers now deliberately mix phosphorus into structural steel. By relying on those same environmental wet-dry cycles, they build shipping containers and architectural facades designed to never require painting or maintenance. Yet recent conservation research from 2026 reveals a vulnerability. While the exposed shaft of the pillar thrives, the 3 feet buried underground are actively deteriorating. Soil moisture traps the iron in a constantly wet state. Without the dry cycle, the armor cannot form, abandoning the metal to aggressive pitting. This subterranean decay was accelerated in the 19th century when conservators wrapped the buried base in a sheet of lead, cutting the iron off from the elements. The iron pillar demonstrates that a monument's longevity can depend entirely on a complex chemical relationship with the harsh elements around it.